A single speck of dust can force an entire wafer worth tens of thousands of dollars to be discarded instantly. That's why the chips you use every day are manufactured in environments almost completely isolated from the outside world, where air is continuously filtered, temperature is tightly stabilized, and even the smallest vibrations are kept under strict control. Behind it all lies a process far beyond conventional manufacturing. Instead of assembling individual parts, a chip is printed directly onto a silicon surface using light. Ultra-thin layers of material are formed, processed, and stacked through hundreds of sequential steps, gradually building a three-dimensional structure with billions of transistors precisely connected to one another. These invisible structures form the foundation that powers everything, from smartphones and vehicles to massive data centers. In this documentary, the Factoran takes you inside the journey of transforming raw silicon into the brain of the digital world. Welcome to TSMC, one of the most advanced technology factories in the world, where some of the most complex engineering systems ever created by humans come together. Here, TSMC produces more than 60% of the global chip supply and over 92% of the most advanced chips, making a large portion of the world's computing power dependent on a production chain concentrated in Taiwan. This dependence has turned semiconductor chips into the center of the chip war between the United States and China. The United States has imposed restrictions to prevent China from accessing sub-5 nanometer technology, while China spends over $300 billion each year importing chips, more than oil. At the same time, Beijing is investing hundreds of billions of US dollars to achieve self-sufficiency in production. In this context, chips are no longer just components, but strategic resources capable of shaping global power. And now put on your full clean room suit. Follow me. We're about to pass through the sterilization chambers and step inside. From this point on, you'll see a system operating almost entirely by machine, where every movement is controlled with extreme precision. Watch closely as we move through each stage to understand how a chip is made. The journey of a chip does not begin inside a factory, but with silicon, an element that makes up more than 25% of the Earth's crust, most commonly found in sand. However, natural silicon cannot be used directly. It must be refined to a purity of 99.9%, often referred to as 9N purity, a level where even a single impurity atom among billions can alter its electrical properties. To achieve this level of purity, silicon dioxide is heated to around 3,600 degrees Fahrenheit, approximately 2,000 degrees Celsius, with carbon to remove oxygen, producing metallurgical-grade silicon. At this stage, a single crystal seed is dipped into the surface of the molten silicon and begins to be pulled upward in a vertical direction. The process unfolds extremely slowly, typically just 1 to 3 millimeters per minute, while both the seed crystal and the crucible rotate in opposite directions to stabilize the internal convection flow. The diameter of the crystal is not fixed in advance, but continuously controlled through temperature and pulling speed. Even a slight change in lifting speed or heating power can shift the diameter by a few millimeters, enough to ruin the entire ingot. Sensors monitor the shape of the neck region from the very first centimeters, as this is the critical zone for eliminating initial structural defects. An important detail throughout the pulling process was the distribution of oxygen from the quartz crucible into the silicon is tightly controlled. When kept within an optimal range, this oxygen improves the mechanical strength of the wafer, but if it exceeds the limit, it can introduce microscopic defects that affect transistor performance later on. The final result is a single crystal silicon ingot measuring 3 to 6 feet in length and weighing hundreds of pounds with an almost perfectly continuous atomic structure. Once the single crystal silicon ingot is formed, it is transferred to a diamond wire sawing system, a thin wire embedded with ultra-hard abrasive particles moving continuously to cut through the material. The ingot is sliced into hundreds of wafers, each about 0.02 to 0.04 inches thick, with tolerances of just a few micrometers. During this process, a portion of the material is lost as silicon powder, and controlling this loss directly impacts production cost. The freshly cut wafers cannot be used immediately. Their surfaces remain rough with microscopic scratches and mechanical stress introduced during cutting. They are ground on both sides simultaneously to achieve uniform thickness, then transferred to a cleaning system. Here, the wafers are immersed in chemical baths combined with ultra-pure water, water that contains almost no ions or contaminants. Throughout the process, wafers are rotated or gently vibrated to ensure uniform contact with the solution, removing all remaining particles. At this scale, even a single particle smaller than 1 micrometer can damage an entire circuit, so the surface must be brought to an almost perfectly clean state before the next steps. At the scale of chip manufacturing, even a particle smaller than 1 micrometer can destroy an entire circuit region. Cleanliness is not just an environmental standard, it is a physical limit that directly determines yield. As soon as processing is complete, wafers are sealed inside FOUPs and transported fully automatically by an overhead hoist transport (OHT) system running along the factory ceiling, moving thousands of wafers every hour without any direct human contact. Leaving the cleaning system, the wafer enters the chemical-mechanical polishing (CMP) stage, where the surface is refined at the nanometer scale. The wafer is placed on a rotating pad and pressed down with very low force, while slurry is continuously supplied. Instead of being ground away roughly, the surface silicon is first softened through chemical reactions, then gradually removed by gentle mechanical friction. The wafer and the pad rotate along different paths to ensure uniform treatment across the entire surface. Rotation speed, pressure, and slurry flow are tightly controlled, as even a small deviation can create variations across the wafer. The amount of material removed is measured in nanometers, yet it directly determines surface flatness and material uniformity. Once completed, the wafer is rinsed to remove any remaining slurry, revealing a surface that is smooth and highly stable. After polishing is complete, each wafer is scanned using nanometer resolution optical inspection systems to detect defects invisible to the human eye. Once it meets specifications, the wafer is sealed inside a FOUP and transported along an overhead hoist transport (OHT) system running across the factory ceiling with speed and routing precisely programmed. A large fab can move tens of thousands of wafers every day fully automatically, and even this transport process is optimized down to the second to minimize waiting time. Before any structure is formed on the wafer, the entire chip already exists as a design created by semiconductor engineers, a process that can take years. A modern chip can contain more than 100 billion transistors, and no one can draw every detail by hand. Instead, engineers design the architecture, define how functional blocks operate, then use specialized tools to implement and optimize the entire system at the nanometer scale. Once the design is complete, it is translated into hundreds of masks, each representing a layer of structures to be formed on the wafer. From this point, photolithography begins, where the entire design is transferred into physical patterns at the nanometer scale. On each wafer, a light-sensitive material called photoresist is applied, with a thickness of only a few tens of nanometers. In simple terms, this acts like a surface for drawing, but instead of ink, the lines are created using light. Each line is only about 5 to 10 nanometers thick, more than 100,000 times thinner than a typical pen stroke. The light used is EUV, with a wavelength of 13.5 nanometers, thus generated by firing 50,000 tin droplets per second into a vacuum chamber and turning them into plasma at temperatures approaching 500,000 degrees Fahrenheit. At this energy level, light cannot pass through conventional lenses, so the system relies entirely on multi-layer reflective mirrors with surface precision, smaller than an atom to guide the beam. The light then passes through the mask, the blueprint for each layer, and is reduced through multiple stages before being projected onto the wafer. Each exposure covers only a very small area, so the entire wafer is scanned section by section, with alignment accuracy between layers controlled within just a few nanometers. If two layers are not perfectly aligned, the transistor will not function. When exposed to light, the photoresist undergoes a chemical change. One portion becomes soluble and is washed away, exposing the underlying material, while the remaining portion acts as a precise template for the next processing steps. In some advanced technologies, techniques such as double or multiple patterning are used, meaning the same layer must be patterned multiple times to achieve the required resolution, significantly increasing complexity and cost. The entire cycle of spray coating and stencil patterning does not occur just once, but is repeated 80 times for each wafer. Each layer is built on top of the previous one, forming an complex three-dimensional structure. Within an area of just a few square inches, tens of billions of transistors are created, spaced only a few nanometers apart, approaching the physical limits of matter itself. What makes photolithography the most critical step is this. Even a deviation of just a few nanometers in a single layer can render the entire chip unusable. This is where the boundary between engineering and the limits of nature becomes razor thin. Right after the circuit regions are defined, the wafer enters the ion implantation stage, the step that determines how silicon will conduct electricity. Here, atoms such as boron or phosphorus are ionized and accelerated toward the wafer at speeds reaching hundreds of thousands of miles per hour. These ions penetrate deep into the silicon lattice, altering the electrical structure of extremely small regions and forming p-type and n-type layers, the foundation of transistors. Afterward, the wafer is heated to repair the crystal lattice and activate the implanted atoms. At this scale, R&D engineers are not just processing materials, they are directly controlling how electric current will flow inside the chip. Once the transistors are fully formed inside the silicon, the wafer enters a completely different stage, connecting them together to create a functional system. Because on their own, transistors are just individual switches, and without interconnects, they are meaningless. At this stage, ultra-thin metal layers are added to form a network of connections. Instead of directly drawing the wiring, engineers use a technique called damascene. First, extremely small trenches are etched into an insulating layer, then metal, typically copper, is filled into these trenches. What makes this challenging is that the width of these wires is only a few tens of nanometers. At that scale, electrical behavior no longer follows conventional rules. Resistance increases, more heat is generated, near-end electrons can even leak through the insulating layer if distances become too small. To address this, the interconnect system is built in multiple layers. A modern chip can have 10 to 15 metal layers, stacked and connected vertically through tiny holes called vias. Viewed in cross-section, the chip resembles a multi-level city where signals move both horizontally and vertically. At this scale, the total length of interconnects inside a single chip can reach tens of miles, all packed within just a few square inches. And this is the key point. Once transistors are created, it is the interconnect network that ultimately determines the chip's real performance, including processing speed, power consumption, and heat dissipation. A great design is not just about the transistors, but how they are connected. Once the entire circuit structure is complete, the wafer enters the electrical testing stage, where each chip is brought to life directly on the wafer surface. Ultrafine probes make contact with each die, sending signals and measuring responses in just a few milliseconds. A single system can test thousands of chips in a very short time, with precision high enough to detect deviations at the nanometer scale. The results are recorded as a wafer map, showing exactly which chips are functional and which are defective. These defects rarely appear randomly. Instead, they tend to cluster in specific regions, reflecting tiny variations accumulated across hundreds of previous process steps. At this level, testing is not just about sorting products, but about reading back the entire manufacturing process. On a single wafer, among hundreds of chips, each small square represents the outcome of one of the most complex technological sequences ever created. From a common element found in sand, silicon has gone through a long journey. Refined to near-perfect purity, pulled into massive single crystals, sliced into thin wafers, and built layer by layer into microscopic structures with nanometer-level precision. Hundreds of processes, thousands of machines, and countless physical controls come together to create something smaller than a fingernail, yet containing tens of billions of transistors. What's truly remarkable is not the size of the chip, but the ability to control matter at nearly the atomic scale to create it. And it is these invisible structures that power the modern world. From the smartphone in your hand to the most advanced artificial intelligence systems. If you want to explore more of the hidden technologies behind everyday objects, follow the Factoran.